Hello everyone, and thank you for attending today's webinar. My name is Jeff Kenvin, and I am the Technical Director at Micromeritics Instrument Corporation. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended today. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm very pleased to introduce today's speaker, Dr. Katarina Peikart. I've had the pleasure of working with Dr. Peikart since she joined Micromeritics in 2016. Prior to joining Micromeritics, Katarina received her doctorate in chemistry at the University of Hamburg, and she has extensive experience with the synthesis and characterization of MOFs, zeolites, and porous materials. Dr. Peikart is currently a technical application consultant, and we are so glad you could be here today to share your insights on best practice for BET surface area.
Thank you, Jeff, and I welcome everyone to this webinar. Today it's all about the BET method, and I called this presentation Best Practice for BET Surface Area. After a brief introduction, I would like to start with the theoretical foundations of the BET model. The main part of this webinar will use real examples to look at how the BET method can be used in the best way possible. Will my carbon black give the best possible performance for my tires? How can I optimize the storage capacity of my battery? Can I guarantee the best performance of my pharmaceutical products? Can I control properties like the strength, texture, and appearance of my ceramic products? Or will my pigments perform optimally in my paints and coatings? What do those questions have in common? I admit, maybe it's a bit of an exaggeration. But generally speaking, in the application areas shown here, such as carbon black, pharmaceuticals, batteries, ceramics, and paints, the essential properties of the end products are related to the BET surface area of the starting materials. And there are many further industries and applications where BET is the standard parameter as well. Additive manufacturing, adsorbents, catalysts, geoscience, and the food industry are some more examples. Before looking at the BET surface area in particular, I'd like to think about what is surface area in general. If we think of a cube or a sphere, like shown here, it is actually very easy to calculate the surface of those bodies just by knowing the geometric dimensions. It has been a while, but I remember learning this back in school, as probably all of us do. If we now think of the samples that are measured every day in our laboratories, it quickly becomes clear that such a geometric approach will not get us very far. There are more corners, edges, rough surfaces, and maybe pores within the materials, so a simple calculation of the area is impossible. Therefore, the idea of using gas adsorption to determine surface areas assumes that the adsorbent completely covers the surface of our material. Consequently, with the knowledge of the amount of adsorptive needed to cover such a surface and the area occupied by an atom or molecule of the adsorptive, the surface area can be calculated. We usually use the specific surface area, so the surface area is related to the mass of the sample. Irving Langmuir was the first person who described using adsorption studies to calculate the surface area of materials. In 1932, he was awarded the Nobel Prize for his studies on surface chemistry. His assumptions were that during adsorption on surfaces, only a monolayer is of adsorbate is formed and that the adsorption is triggered by an inelastic collision. In a simplified way, we can describe the adsorption process as shown here. We start the adsorption measurement at low pressures. At first, single molecules or atoms are adsorbed at isolated sites on the surface of the sample. We now know that the surface of most materials is not homogeneous, and there are sites where adsorption is preferred due to stronger interactions. This had not been considered in Langmuir's work. At a certain pressure, the point is reached where the entire surface is covered with adsorbate. And exactly at that point, according to Langmuir, we would have reached the end, no matter whether the pressure is further increased or not. Brunauer, Emmett, and Teller extended Langmuir's model, finding that further adsorption can occur on the first adsorbate layer. We are talking here about multilayer formation or multilayer adsorption. Their work on adsorption of gases in multimolecular layers was published in 1938. And in contrast to Langmuir's work, beside the multilayer adsorption, they describe the condensation enthalpy as driving force of adsorption. Meaning, in the adsorbed state, the adsorptive can be seen as a liquid film, then called adsorbate. The BET model is a more realistic case compared to the Langmuir model. However, it also comes with some simplifying assumptions. Beside the multilayer adsorption, Brunauer, Emmett, and Teller consider the materials under investigation to show no porosity and to be homogeneous. That means there are no different sites. All adsorption sites show the same interaction energy. 2 slides back, I already explained that we now know this is not true. They also say that the adsorption energy of the first layer is larger than of the following layers, independent from the degree of coverage. And the adsorption energy starting from the second layer corresponds to the condensation energy of the bulk. One last assumption, the interaction between adsorbed molecules can be neglected. What they consider more important is the interaction between the adsorbed molecules and the surface. What do those assumptions mean in terms of applicability? Having the different types of isotherms in mind that are described by UPAC, the BET model is applicable for type 2 isotherms, those of non-porous or macroporous materials. It could be demonstrated that in mesoporous materials, we can still assume the formation of multi-layers of adsorbate, and the BET model can be also used to analyze those. Whereas in microporous, the BET equation is strictly speaking not applicable. Here, one layer of adsorbate can easily touch 2 opposite walls, depending on the pore sizes, of course. And due to overlapping adsorption potentials of opposite walls, the adsorption energies of microporous materials are much higher than those of meso, macro, or non-porous materials. I will describe later in this presentation how the BET model can be used with microporous materials. Having heard of multilayer adsorption and adsorption energies, how does the BET model calculate surface area? To calculate the surface area, we need to use the adsorption data to determine the amount adsorbed in a statistical monolayer. The BET equation describes the volume adsorbed, VA, as shown here, as a function of pressure, volume adsorbed in a monolayer, and the empirical constant C. The equation can be transformed into a linear form, and now we can see nicely that by knowing the adsorbed volume VA at the related relative pressures from our analysis data, the monolayer capacity VM and C can be calculated from the intersection with the y-axis and the slope of the fitted data. The corresponding graph is called the BET transformation plot. It is important to note that the linearity does not apply to the whole range of the isotherm. Therefore, for data reduction, the linear range of the BET plot must be chosen. For non-porous, meso and macroporous materials, this range is typically between relative pressures of 0.05 and 0.3. I am regularly asked what the C constant is all about. It accounts for the adsorption enthalpy of the first layer and the enthalpy of condensation. That means, depending on how strong the interactions are between the surface of our material and the adsorptive, we get different values for the C constant. The stronger the interactions, the higher C. For nitrogen at 77 Kelvin, values between 50 and 300 are common. Materials with especially weak interactions show lower C values, whereas microporous materials show larger values due to the high adsorption enthalpies. Today we focus on BET surface area, but as you all probably know, we can use the gas adsorption data, so the adsorbed volume versus pressure, to also calculate pore volume and pore size distribution. This hypothetical isotherm refers to a material with micro and mesopores, so it's a combination of the type 1 and type 4 isotherms. I'd like to use it to illustrate which pressure ranges are relevant for different adsorption phenomena and therefore the corresponding calculations. Depending on the pore size of our material, a complete isotherm is collected starting at relative pressures as low as 10 to minus 9 and up to relative pressures close to 1. The adsorption process begins at very low pressure in the micropores. The limiting uptake here is related to the accessible micropore volume rather than by the internal surface. The magnitude of surface area is directly related to the pore size and the available pore volume. By increasing the pressure, we reach a region where the monolayer multilayer adsorption on the pore walls takes place. This is the range also referred to as BET range. And we need the data points from exactly this range for the BET calculation. If the surface area of our samples is the only relevant parameter, it is common practice to not collect a whole isotherm, but just a decent number of data points in the BET range. This can save a lot of time. Especially in the early days, a single point BET was very common. When time is the crucial part, like for instance in production control, this allows the determination of the surface area within a couple of minutes. More reliable is multi-point BET. Here we find, for example, 3-point, 5-point, and 10-point BET. The BET method is also part of several standards like the DIN ISO 9277, the ASTM C1069, or D6761, and many more. In addition to the gas-solid interaction, we now observe also the gas-gas interactions, followed by the condensation of the adsorbate in the liquid-like phase. This phenomenon is named capillary or pore condensation. When all the mesopores are filled by the liquid adsorbate, the isotherm typically reaches saturation, and a plateau is reached before reaching the real saturation pressure. At this point, the adsorbed volume can be used to calculate the specific pore volume for the detectable range, so for all pore sizes that would fill at this pressure. Typically, the Gurwitch rule is used for this calculation, and an important condition for meaningful determination is a well-defined saturation step. Some of you are probably very familiar with isotherms that don't reach such a plateau. This is the expected scenario for materials consisting of micropores. If this is the case for you, it might be worth considering using mercury intrusion porosimetry as supplementary analysis method. Let's get back to BET surface area. What are common values to expect here? The range that results from different materials extends from less than 1 square meter per gram to several thousand square meters per gram. Pharmaceutical products tend to show low surface areas. Values can be easily lower than 1 square meter per gram. For lactose, a typical pharmaceutical binder, for example, I have seen BET surface areas between 0.05 and 5 square meters per gram. Carbon blacks can show BET surface areas between 30 and 300 square meters per gram. Silica gels are an example for relatively high surface areas of about 600 to 850 square meters per gram. And the highest surface area materials are microporous materials like zeolites, activated carbons, and metal organic frameworks, also called MOFs. The two MOFs, NU109 and NU110, are reported to show BET surface areas of up to approximately 7,000 square meters per gram. That means 1 gram of sample would cover about 1.5 American football fields. As the title of this webinar is Best Practice BET Surface Area, we definitely want to look at the parameters that influence the quality of our BET measurements. I would say it already starts with sampling. How representative are the few grams or even milligrams that are used for the experiment for a whole batch of material? We know this from cereals. The big chunks are always on top. So a well-mixed representative sample is therefore important for the measurement. Other important parameters are sample mass, sample preparation, the setup, so the type of sample tube, using a filler rod or not, the kind of adsorptive and instrument, and the analysis parameters itself. I would like to use real examples now to give you a guide about how to use these parameters in order to optimize your adsorption measurements. Let's get started with the Mesoporous silica alumina. This is one of our reference materials. I mentioned earlier that we can either use the data points from a BET range of a complete isotherm, like we see here. I highlighted this BET range in gray. Or alternatively, we just collect several data points in that range, like shown here. In this case, it is a 7-point BET measurement. Applying the BET equation and plotting it in the linear form is luckily something that the instrument software does automatically. We see again the comparison of the two experiments. On the left side, the plot using the corresponding data points from the isotherm, and on the right side, the 7-point BET data points plotted. I used the same sample mass for both experiments, and we can see the resulting BET surface area is nearly the same. 203.56 square meters per gram versus 203.35 square meters per gram. The correlation factor, R squared, reflects how well the BET equation applies to the data set. The closer this value gets to 1, the better the fit. And the C constant shows a similar magnitude for both measurements as well. The calculated amount adsorbed in the monolayer is just under 47 cubic centimeters per gram for each of the two measurements. This was a straightforward example. Let's see it as kind of a warm-up. The second example I brought is a zeolite, so microporous material. I already mentioned that strictly speaking, BET is not applicable for those microporous materials. We see here a 10-point BET measurement, and the data points were collected in the classical BET range, so between 0.05 and 0.3 as relative pressures, just as in the example of the Mesoporous silica alumina. In contrast to the previous example, the isotherm of the zeolite is nearly flat, while showing already high quantities adsorbed of around 250 cubic centimeters per gram. For the silica alumina, we were in the range of 50 cc per gram as quantity adsorbed. Looking at the BET transformation plot, what we typically observe when applying the classical BET range to microporous materials, like this zeolite Y, is a negative intercept with the Y-axis, resulting in a negative C constant. And that is something which is physically impossible. Looking at the complete isotherm for this material, we also see from a graphical point of view that the isotherm is already saturated in the considered BET range. What we already saw in the 10-point BET measurement as being really flat. So even if we could think of a stage where a monolayer inside the micropore is established, that would have been the case at lower relative pressures. Despite the discussed limitations, it has become common practice to apply BET for microporous materials as well. But this is not as straightforward as with other materials. Rockerole, Llewellyn, and Rockerole first published in 2007 some criteria that must be fulfilled when using BET for microporous materials. Those criteria were also adopted by the UPAC report regarding physisorption of gases and standards like the already mentioned ISO 2977. First, beside the BET plot being linear, as already mentioned, the C constant must be positive. Additionally, when plotting the term N, which is the adsorbed volume times 1 minus the relative pressure versus the relative pressure, the resulting graph must be continuously increasing in the selected range for data reduction. This we refer to as Rockerole plot. Furthermore, the monolayer capacity Nm should be within the selected data range and not an extrapolated value. And the last criteria is that the relative pressure value that corresponds to the monolayer capacity should be within 10% of the calculated value. Otherwise, it is necessary to change the chosen range of relative pressures. I want to emphasize at that point that those criteria must be fulfilled actually for all BET calculations, not just in the case of microporous materials. It simply is the microporous materials where the classical BET range gives invalid results nearly all the time. This is how the BET data reduction window looks like in the Micromeritics software. Beside the BET plot on the upper left side, which must reflect the linear range, the software also shows the rock and roll plot on the lower left side. Therefore, the first three criteria can easily be checked. For our example, we see that using the classical BET range between relative pressures of 0.05 and 0.3 will not give us continuously increasing values for the rock and roll plot. And this shows that taking data points only in this range is not sufficient for microporous materials. What we need to do is to extend the range to lower relative pressures. Something I like a lot is the use of an AutoBET script that our software offers. You can find that in the advanced report options. The script does an automated BET calculation and it checks for all the 4 criteria, like we can see here. For our zeolite example, the data points used for the BET calculation were taken between relative pressures of about 0.003 and 0.03. So we see it was shifted to lower relative pressures in comparison to the classical BET range. Let me summarize at this point what is important when analyzing microporous materials. Extend the pressure range so that you have enough data points to define a valid range for BET data reduction. Collecting a whole isotherm might be a good idea here as well. Check for the 4 criteria by looking at the C constant and using the rock and roll plot and or the AutoBET fit. Don't use too much sample mass. Microporous materials typically have large pore volumes and adsorb large amounts of adsorptive. So having too much sample in the tube will lead to longer analysis times. Having a stable free space is a critical factor in the experiment. And Micromeritics isothermal jackets technology offers a simple but ultimately highly effective way of maintaining a stable free space over the time scale of the experiment. The next example is a polymer. Using about 900 milligram of sample, we get this isotherm. As you can see, it's not the most beautiful one, and we don't get a smooth increase we expect to see. The BET plot is also not as nice as seen on the previous examples. This is reflected in the correlation coefficient. The surface area is very low at about 0.25 square meters per gram. I repeated the test with about 3 times the sample mass. This leads to a much nicer isotherm, and the BET plot now looks nicely linear. In the static manometric method, the volume that is adsorbed is calculated using the measured pressure differences. If we have only small absolute surface in our sample tube due to low sample mass and small specific surfaces, the pressure difference that occurs after adsorption is very small. In this case, a higher measurement accuracy can be achieved by using larger sample quantities. Here we see another low surface area material, a wood sample. With about 1 gram of sample, and that is all I could fit inside the tube, I performed a 10-point BET measurement. The resulting isotherm shows a slightly decreasing amount of quantity adsorbed with increasing pressure, resulting in this curved isotherm. In order to get a valid BET value, only the 3 first data points could be fitted. There are different reasons that can lead to such a negative trend in the isotherm. A leak or insufficient degassing are 2 examples. A change in analysis temperature leading to a change of free space or error in the free space measurements itself can also cause such an effect. Another reason might be insufficient equilibration. In this case, using a different instrument was the solution for our problem. I used our Gemini, which has a different way of operating in comparison to other standard static manometric systems. It uses a reference or balance tube, which is connected with the sample tube by a differential pressure transducer. Changes in external factors such as evaporation of the cryogen or non-ideality of the gas are compensated for as the balance tube is in the exact same environment as the sample tube. Dosing by the use of a servo valve controls the rate of gas flow into the sample tube to accurately obtain target pressures without pressure overshoot. By this, the Gemini allows high accuracy, especially for low surface area materials. Looking now at the results obtained by the Gemini, we see a significant difference to the standard measurement. The standard measurement shown in green, the Gemini measurement shown in red, yielding a specific surface area of 0.98 square meters per gram and a nice BET fit over the whole BET range. This example shows that with some low area materials, the Gemini can be the preferred way of running and offers unique advantages over other static volumetric technologies. A similar, even more drastic behavior was obtained for this pharmaceutical binder. This time using nitrogen at 77 Kelvin, neither with the standard instrument like our TriStar nor the Gemini gave good results. The isotherm shows a completely decreasing behavior. Trying to use this isotherm to calculate BET gave this funny looking BET plot. There was simply no way of getting a valid fit. The first thing I did was of course checking for leaks and repeating the tests. But I could only get a reasonable result after changing the adsorptive from nitrogen to krypton. Red shows the krypton isotherm and in green we have the nitrogen isotherm. The BET plot now shown is the one from the krypton measurement. You see it's a nice linear fit and we obtain a BET surface area of about 0.17 square meters per gram. Why did this work with krypton and why is krypton an alternative for nitrogen adsorption? I mentioned in one of the previous examples that it can be difficult to resolve only small pressure differences well enough for small surfaces. At 77 Kelvin, the saturation pressure of nitrogen is 760 torr. In comparison, krypton has a saturation pressure of only 2.5 torr, which is much lower. This means that at an identical pressure, there are considerably fewer krypton atoms in the gas phase than nitrogen molecules, and consequently, a correspondingly larger pressure difference occurs after the adsorption process. Due to the lower pressures, we need a higher vacuum for the instrument, so a turbo pump is used, and a higher resolution pressure transducer, 10 torr instead of only 1000 torr, is also required. This is a theoretical calculation example that illustrates the difference we get between nitrogen and krypton. Don't worry, it sounds more complicated than it is. Let's imagine an absolute surface of 1 square meter in a sample tube of 20 cubic centimeters of volume. With a relative pressure of 0.2, we can calculate that the sample adsorbs 0.287 cubic centimeters of nitrogen or 0.222 cubic centimeters of krypton. At these conditions, an amount of 14.144 cubic centimeters of nitrogen remains in the gas phase above the sample, referred to as TP, compared to 0.046 cubic centimeters of krypton. Consequently, a total of 14.431 cubic centimeters would have to be dosed for nitrogen in the experiment, of which 98% would remain in the gas phase and only 2% would be adsorbed by the sample. For krypton, 0.268 cubic centimeters would have to be dosed, and here 17% remain in the gas phase, while 83% would be adsorbed. It is quite obvious that there is consequently a significantly greater pressure difference for krypton. To sum up the low surface area chapter, I brought some advice. Use as much sample as possible, but work with the minimum tube size. Reduce the free space. This can be done by using filler rods and sample tubes with smaller stem diameters. The smaller free space guarantees a lower volume of gas in the gas phase and hence increases the pressure difference in the adsorption. With the Gemini, low surface area materials can be analyzed with nitrogen more precisely than with other gas adsorption instruments. And krypton is the adsorptive of choice for really low surface areas when no meaningful results can be obtained using nitrogen. There is one last topic I would like to address in regard of best practice BET surface area. This one is the importance of the right sample preparation. In order to provide a clean and dry surface, samples are typically degassed before the adsorption experiment. Degassing takes place either in vacuum or in inert gas flow. Times and temperatures can be varied. It is mainly water adsorbed on the surface and in the pores of the material that needs to be removed. The right degassing procedure has a huge influence on the results we get from the adsorption experiment. This example here illustrates nicely how the temperature can relate to the BET surface area. A carbon material was degassed in vacuum for 30 minutes at 50, 150, 250, and 350 degrees Celsius. We see that with increasing degas temperature, we observe increasing surface areas from 172.5 up to 211.5 square meters per gram. The thing is, just from looking at the adsorption results, it is not necessarily obvious whether the right degassing conditions were used or whether the degas was insufficient. Varying the temperature is one way of optimization. Longer degassing times can also be the solution. When working with new materials, I just highly recommend to take some time in order to find the optimal sample preparation conditions for your material. This brings us to the end of this webinar. I would say specific surface area is the most widely used parameter to be achieved from gas adsorption. It is used in many different industries as one of the key material characteristics. And it is worth asking the right questions in order to get the most out of your BET measurement. I hope that I could give you at least some ideas and suggestions for answering just these questions. By this, I thank you all for participating, and I'm happy to answer some more questions now.
Thank you, Katerina. I'm opening the chat for everyone's questions now, and we already have a few. The first question is really practical. For preparation, how do I know if I should use flow or vacuum?
Yeah, that is indeed a good and practical question. In general, I think we can say that both methods are good working procedures. And of course, it depends a little bit on your materials. It depends on time. It depends on the surface of the material. In both, what we try to get is a clean surface. And from a practical point of view, in my experience, actually, it's sometimes even more important how I handle the tubes after the degassing. So when transporting from the degas device to the instrument, rather than what type of degas I use. Also, maybe as a really practical advice in terms of different kinds of materials, from my experience, you see a lot the flow being used for carbon materials. And on the other side, you see that for microporous materials, people like the vacuum over the flow. If we compare what the different methods do, one thing that might be an advantage in the flow is that we have like a second driving force, not just the difference in concentration from the molecules being on the surface, like water or CO2, being desorbed from the surface into either vacuum or the inert gas. In the flow, we have as a second driving force that the inert molecules like nitrogen continuously are striking the surface of the material, so causing another momentum for the molecules to be desorbed. So that can lead in general to faster absorption rates. That is something you might want to consider But you see for many materials that both techniques work very well and are kind of comparable to each other. You find in the material that is provided for this webinar also an application note where exactly this topic is discussed, so maybe that helps for getting more information about this question or this topic.
Second question is similar in being very practical in how people develop their BET surface area data. How many data points should someone use? What's the minimum for a BET surface area measurement?
Yeah, that is actually a question which is constantly discussed, I would say. And I referred to some standards. So depending on where you look at, you find different recommendations. The ASTM 6556, which deals with carbon black and how to measure BET surface area for carbon blacks, for example, says a minimum of 5 data points, and the equivalent BET range is recommended. If you read the book Adsorption by Powders and Porous Solids, which some of the authors are Rockerole and Llewellyn, I mentioned them in terms of the criteria to be used for BET. They clearly state that at least 10 points should be used as a minimum. So you see there's no clear answer. I personally would also say at least 5, but 10 is probably even better. So if you have the time and you can take 10 data points, I would definitely go for that. But on the other hand, sometimes time is the issue. For example, in production control, maybe those couple of minutes save are more important than the high accuracy you might get with more data points.
So I'm going to bundle 3 questions together because they all fit very nicely together. And the first one is, what happens if I get a negative C value? How should I adjust my calculation? And what's the best range of relative pressures that should be used?
Yeah. I think what you probably have seen with the examples that I used is that it's not always straightforward to find the right range, and it depends on the materials. It depends on the quality of the isotherm, and there are different influences to the quality of the isotherm. So as I mentioned, what I really like is the auto BET fit, because it kind of does the work for you. It helps you to find out for this material, for this set of data points, what is the right range so that I can make sure that the criteria that I mentioned are fulfilled and met in a perfect way. And so I would use that as the answer to those 3 questions. It makes a lot of things just as easy as possible for you.
When you use that method, what are the criteria in there of that method and sort of some of the general methods that you refer to, the ISO methods and ASTM, when you look for misfit or correlation? What's the best? What do you typically recommend for someone when they're judging how well BET fits their data?
I'm not quite sure if I understood that question, to be honest.
So maybe when we look at the statistics that are there that are given, typically the R squared is reported for how BET fits the data. What's the minimum there that people should consider using as acceptable for their result?
Yeah, that goes into a similar direction, like what I said to how many data points are recommended to be used. You find different opinions here. I know that some people say you should have at least 4 nines after the decimal point. My feeling is, and my experience is that sometimes the difference is not that huge, depending on whether you have 3 or 4 or even 5 or 6 nines, so getting closer and closer to 1.
yeah, this is what you read, aiming for at least those 5 nines. I don't know. Maybe you, with having even more experience, Jeff, have some additional advice to this question.
No, I know. I think that that kind of direction is really perfect. That, you know, as we look at how the BET model fits the experimental data, I think being very reasonable and using criteria like you had mentioned is the right direction. It's really the best.
Yeah.
The next question gets back to being really practical again, with how the experiment is conducted. What could happen with free space if you don't use a filler rod, and how could that possibly affect things?
Mm-hmm. I saw that the filler rod question was asked in regard of the microporous materials as well. So maybe it's good to say a couple of more things about the filler rod. So we have to look at the scenario that we have. So again, it depends a lot on your samples. If you have low surface material, then we just see that the small amounts of gas being adsorbed during the adsorption process are sometimes so low that everything happening in the background, like the gas behaving not idle in the gas phase above the sample, can have a stronger influence in comparison to what you see in the adsorption. And that is what we always try to minimize for low surface materials, so that we see the adsorption process being more dominant and prominent than the background noise. Let's call it maybe background noise. Might not be the perfect description, but yeah, we need to see enough change during the adsorption. And one thing to optimize this is minimizing the free space. So that is why we use the filler rods for low surface area materials, so that we just get a better accuracy. And what could happen if we don't use it, of course, is strange effects with just the non-idle behavior of the gas in the background being more prominent than the adsorption process we see. If we now look into the other direction with microporous materials, we typically have surface areas high enough so that the pressure change that we detect is large enough to cancel out the background things happening. And I said that we recommend not to use the filler rod here, mainly because of the thermal transpiration correction. Some of you might have read this, have come across this in the software. This is something that matters in the really low relative pressure ranges. And this is a correction that accounts for the pressure gradient in the tube. So closer to the sample, we have slightly different behavior than on the top of the tube. And this correction correlates to the diameter we have inside the tube. So we enter the tube diameter in order to apply the right correction, and that is something where the filler rod will change the scenario. So that is why we recommend not to use the filler rod. If you don't need the thermal transpiration, as I said, it's for the range where the micropores fill, so in the really low relative pressure range. But if that is not relevant for you, then the filler rod will not cause any mistakes or errors here. It just makes this calculation less accurate. And as I said, the amounts adsorbed are typically in a range where we don't have any issues with the non-IO behavior and other background things happening, so that here the filler rod is not as important as for the low surface area material.
Thank you. The next question gets back to maybe something really important that we often don't discuss when presenting adsorption information. Can you tell the audience what STP stands for when they look at the plots?
Yeah, sure. STP stands for standard temperature and pressure. And we use as standard temperature 0 degrees Celsius, so 273.1 Kelvin, and the standard pressure is the ambient pressure. And during the measurement, we of course don't have the standard values for pressure and temperature, but the volumes adsorbed, the volumes calculated, volumes inside the instrument, this is all referred to those standard settings or standard values for pressure and temperature. So it's recalculated so that it applies to this temperature and this pressure.
Okay. Next question, again, very practical with respect to perhaps your last few slides when you were talking about preparation. What's the optimum time for degassing, and how can we determine that?
Yeah, the optimal time is, I would say, that point where further increasing the degassing time would not lead to a further weight loss. And that is one way how you can determine whether you already are using the right ways, the right times. The example I showed was changing the temperature. You can do the same with varying the time. So if you know one temperature is the right temperature for your material, start with 30 minutes, go to 60 minutes, 2 hours, and so on. And you can either collect isotherms after each time and compare the BET results. But a first hint, which is less time consuming, could be that you just check the weight change. And if the sample mass is still changing and you still get lower sample masses, that's also a good indication that you would need further increasing in order to completely activate your materials.
The next question is really similar. Again, it gets back to toward the end of your presentation and talking about preparation. You had mentioned handling of the sample tubes and influences there. What's considered proper or improper when you're handling sample tubes and moving from preparation to the analysis?
Yeah. So one thing I would never do is leave the sample tube open or just putting your thumb on top of it in order to close it. You know from the instruments and the accessories that all the sample tubes typically come with a rubber stop. And my experience is that if you quickly close it with this rubber stop, then you determine the sample mass and you put it to the back or on the instrument. That for many materials this works quite well. So you don't always need a special equipment or a special seal fritz or check seals. Those are also available, and it depends a lot on how sensitive the materials are in regard of reabsorbing CO2 or water or moisture from the atmosphere. What I think some people might not have in mind is that that time is a key here as well. So what I typically would never do is get the sample tube off of the degas station, put it aside, wait for a couple of hours before I then put it to the instrument. That's something I would avoid because then the rubber stop is not closing tightly enough. Here it would be recommended to use those seal fritz or check seals. They close in a better way. But in general, I think you could time the degassing and starting the analyses in a way so that you just do it right after each other. So you get it from the degas station to the weight, the balance, and then to the instrument. And my experience is that for most materials that works well.
The next question is a bit material specific. For microporous materials, what points should be used for BET, or should someone use dubinin rather than BET?
Yeah, so what points is something that we can't answer in general because it's not the same pressure range for all microporous materials. Here again, I would recommend using the auto BET. The dubinin, I must admit, I'm usually not using that that often. So I'm not sure whether it's a good alternative. You see that with applying the criteria, the BET is frequently used for microporous materials, and the good thing is that with the rock and roll plot, it's easy to determine the right range. As I said, it can vary for the different materials or different microporous materials. And as far as I know, the Dubinin is quite material dependent, so it's not a general method. But I'm not 100% sure, I have to admit.
Is there again another really practical preparation question? Is there a minimum degas temperature to be used for materials for preparation?
There is typically not, or I would say there is not. We always try to be at least a little bit about room temperature, so in the range of 25, 30, 35, so that we can make sure it's a stable temperature. But yeah, we get materials quite on a regular basis where the people know that they are temperature sensitive and that we can only use conditions close to room temperature. So that's something you actually see. It's not like 50, at least 50 or 80 or something degrees Celsius would it. We can do degas near room temperature.
Here's another really interesting, again, all the questions have really been great today. What happens for some materials if you get two zones when you look at the Roquerol plot? How do you choose if there are two zones on the Roquerol plot for a surface area sample?
Yeah, for some materials that can happen. I've seen that before. What you can do for checking if you're in the right range, it's not always clear, not always straightforward, but I've seen those two linear ranges and rock and roll ranges, or it was linear. I don't know if it's two rock and roll ranges, to be honest, but sometimes you see that if you have two different pore sizes, so for example microporous and then also mesoporous, with two different ranges of pore filling. And what you don't want to do is apply the BET plot in the range where mesopores are filling. That can sometimes be a linear range, but in that range we know that we are not in the range of multi-layer adsorption. And so a good reference is trying to find the point where the monolayer, multi-layer adsorption takes place. And you can, in most cases, if you collect a whole isotherm, you can see from just the shape of the isotherm where this is likely to happen. But sometimes it's not straightforward. There might be even materials where there is actually not a clear, valid BET range. That can also happen. For some materials, you can have a hard time finding the right BET range or even finding one at all.
So this is a shift from microporous materials to mesoporous materials. How do you calculate the surface area for mesoporous materials?
Yeah, for most mesoporous materials, you see that the BET range that was classically proposed by Brunauer, Emmett, and Teller in the range of 0.05 up to 0.3 as relative pressures, that range applies very nicely to most mesoporous materials. But you can use the auto BET fit in the same way as using it for microporous materials. It doesn't distinguish between the kind of material you are using, actually. And as I mentioned, those 4 criteria are valid for all materials and help you no matter what kind of material you have to find the right range.
Is there a case with low surface area materials that you have to adjust the relative pressure range for the BET determination?
Yeah, that can also happen. What I see quite frequently is that you have to shift a little bit to lower pressures, so maybe going up to 0.2 instead of 0.3. So you would just take off the last pressure points because they would not fulfill the rocker roll plot or the increasing range of the rocker roll plot.
This, I think, gets back to earlier in your presentation. You had discussed materials and the C value. Someone asked, how large can the C value be? You know, is there a maximum for that particular constant?
That's a really good question. I never thought about that. I think I've seen values above 1,000, but I don't know if there is a maximum. I've never heard about a maximum value. But what you see definitely on a regular basis is several hundred. And as I said, I think I've seen values above 1,000, but
yeah, I think there was some very old literature that people had recommended certain ranges for the C value. But as materials have improved and the ability to synthesize new materials has exploded, and just a phenomenal new materials available, I think we see the C value really ranging to very, very high values now. And basically, as you see that C value, as long as it's positive, that's a very good indicator. And seeing values in the thousands is not uncommon anymore because of the new moths and other microporous materials. So I think there's no maximum. I don't think we would consider a maximum anymore. Is there a good way to determine about overheating a sample? And you know, should we be careful about the maximum temperature of degas? And then also, is it better for a short degas time or a long degas time, kind of trading time and temperature?
Yeah, that's again not easy to answer because it depends so much on the different materials. But you can have degassing times being, degassing temperatures being too high. Not in regard of the results you might get from the BET surface calculations or the isotherms collected in general, but what can happen to your materials, of course, is a change of structure, a change of morphology. You can see phase changes occurring depending on temperatures, and that, of course, is something that you want to avoid unless you want to analyze the material in that sintered state or new phase state or whatever. So what I usually do or what I recommend to do is get additional information about your materials. What do you know from the literature? What do you find out, for example, if you do TG analyses that can help you a lot to see what's going on with your sample, how it behaves in terms of different temperatures. So all sorts of additional information from other analytical methods that help you to know and to be sure that temperature using for degassing is the temperature where you don't change the sample in kind of or in terms of the structure or morphology. And then for degassing the sample, if you know that the temperature won't harm your sample, then when it comes to the time, I wouldn't say that there is a time too long. If it's clean, if everything is desorbed and you would treat it even longer, it shouldn't harm your sample unless, as I said, some structure changes might occur. And that's something we definitely want to avoid. But this is difficult to find out just by looking at the results from the gas adsorption. So here, definitely, I think it's recommended to use additional techniques.
Thank you, Katarina. That's all the questions we have time for today. If we haven't been able to get to your question, one of our application team will be in touch shortly. Katerina, is there anything else you would like to mention?
Just thanking you again for participating, for your attention, and I think we're still at the beginning of our webinar series. There are a lot of other nice topics where we will have webinars in the upcoming weeks, so I hope to see some of you again in one of the other webinars, and have a nice afternoon or rest of the day depending on where you are.
Great. Thank you for participating in today's webinar. If you have any feedback for us, we would be grateful if you could complete the survey, which will be distributed in our follow-up email. We hope you found the session beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to welcome you again soon. Thank you all. Have a great day.